Okay, so this part of the diagram, we are going to be looking at the four main components. So our compressor being number 1, the condenser being the number 2, the metering device being our number 3. See, I don't know why it does that. And then our evaporator being number 4. Okay, nice tails on those numbers. So the four main connecting pipes. So we have, let me do a different color quickly. Our four main pipes. Yeah, let's stay with that. Our four main pipes. So we have the hot vapor line. All right, here. The hot vapor line is, as said, it's hot. It will burn your hands if you touch it. It contains vapor. So hot vapor is what's in that pipe. Then we have the warm liquid line, which is down here. So leaving the condenser and passing into the expansion device, metering device, is liquid. It's desirable to have liquid, and although it's a subcooled liquid, desirable to have a subcooled liquid, it will be warm. It will be a little bit warmer than ambient temperatures. And it will be a subcooled liquid. Sorry, just getting rid of the noise. Okay, so the next one, the cold mixture line. As the refrigerant passes through the expansion device over here, it goes from high pressure to low pressure. Gee whiz. Okay, so we go from a high pressure side to a low pressure side, and that creates a change in temperature from high temperature to low temperature, or from warm to cold. So coming out of this pipe on that side is our low pressure, low temperature saturated mixture. So that's the cold mixture line. Some vapor, mostly liquid. Passing through our evaporator, absorbing heat, boiling, and this boiling happens at very low temperatures, okay, depending on the system. So we will then have 100% vapor leaving our evaporator on the way to the compressor. It would be cold, in some cases well below 0, depending on the systems. If you're operating a refrigeration freezer system, you're going to have maybe minus 18 degrees in your evaporator, a little bit of superheat, you're still going to have minus 12 and colder in this pipe coming back. So that pipe is going to be pretty damn cold. Okay, direction of flow, you can see we've indicated the direction of flow in our diagram. So clockwise direction of flow. I can divide the system high pressure and low pressure side. So there's my high pressure side and there's my low pressure side. So the compressor and the expansion valve are what are used to identify the high pressure and low pressure sides. Condenser will be in the high pressure side, evaporator will be in the low pressure side. Great, moving on. Okay, so we have said that we have coming out of the compressor high pressure, high temperature, superheated vapor. That's coming out of the compressor and then it's passing into the condenser. In the condenser, the refrigerant needs to condense. It does not instantly condense. So as it goes into the condenser, we're going to have a certain amount of what we would call de-superheating. Once the refrigerant has reached the temperature where it will condense, condensation will take place. So condensation will occur until we have at some stage 100% liquid in the condenser. If it is still passing through the tubes of the condenser and cooling is applied across the condenser in the form of, let's say we have a fan that is blowing cool air across here. You have a fan with a motor blowing the cool air. The air comes out warm. Okay, so the air is going to leave warm, and that air is picking up the heat from the refrigerant. So that air passing through the condenser will still cool down the last part of the condenser where this liquid refrigerant is still traveling, and that would allow us to have a certain amount of subcooling. So the refrigerant leaves the condenser. It is still on the high pressure side. Okay, it is still high pressure, high temperature with a little tail on it, and we now know that it should be a sub-cooled liquid. Okay, and that's what's arriving at the expansion valve. So the compressor is only handling superheated vapor. That's all the compressor wants. Liquid coming to the compressor will kill it. So to plot the compressor on our temperature enthalpy chart, we will put our compressor, doesn't matter where, but the compressor will be over here. Okay. There's our compressor. We are then going from the compressor to the metering device, the expansion valve, and the expansion valve likes to see subcooled liquid. So subcooled liquid is on this lower section of the graph. So we can draw our TXV. It can be any metering device. And the TXV receives the subcooled liquid at a high pressure and a high temperature. Okay, so the high pressure we're going to get from our system by means of a pressure gauge, but we need to remember that this is an absolute pressure. Okay, and that high pressure from the vapor tables, whichever vapor tables we are using, will give us the corresponding saturation temperature. Okay, and that is the temperature that will be happening inside our condenser. Where the condensation will be taking place. So again, from a pressure gauge, we will get the high pressure. From the high pressure side, we need to go to our vapor tables to get the saturation temperature. What we need to do is to be able to measure the temperature after the condenser. So that would require a temperature sensor of some sort. So we would have a temperature gauge mounted or temporarily installed to measure the temperature. The temperature indicating a subcooled value would be plotted on the graph. So T subcooled, and that would be the last part of our condenser. So you can see that the subcooling actually provides us with a little bit more heat transfer to be able to get rid of a bit more heat energy. The more heat energy we can get rid of on the high pressure side, the more heat energy we can absorb on the low pressure side. Okay, but what I'm trying to show you here as well, by having the drawing to this kind of scale, is that the main way we are moving heat energy is by means of this latent heat energy transfer. Okay, which is a much greater amount of heat energy. So the latent heat energy transfer is increased with sensible heat energy transfer, and that would be the total heat energy we reject. Gee whiz, man. The total heat energy rejected in the condenser. And that heat energy will be carried away by the cooling medium, whether it's cooling water or cooling air. Okay, coming back to the entry of the condenser, plotting the de-superheating. Okay, so the vapor does not just instantly condense. It has to cool down to the condensing temperature, which is there. So this first amount of heat being removed is a small amount of sensible heat transfer, and we can see that the total heat energy is greater. It's made up of the heat energy cooling down the vapors, the heat energy converting the vapors to a liquid, and then the heat energy cooling down the liquid. Right, let's move along. Okay, the low pressure side, we're going from our expansion device, our TXV, and we are moving through the system to our compressor. So we're now on the low pressure side. Coming out of the expansion device, metering device, we're on the low pressure side. We're on the low temperature side, low pressure, low temperature, and this is the saturated mixture. The saturated mixture enters the evaporator, and as it passes through the evaporator, it evaporates, boils away, turns from a liquid to a vapor. At some stage, we end up with 100% vapor in the evaporator. Heat energy from the cold room is still being applied to the refrigerant. And this heat energy, we have a fan, and the fan is passing the air around the cold space and passing it through the evaporator. So the heat energy from the cold room is being absorbed into the refrigerant in the evaporator. Okay. And once we have this very cold refrigerant that's turned into a very cold vapor, the vapor is cold enough, it still will absorb heat energy. So the vapor will tend to warm up as it passes through the last part of the evaporator. This will then be a certain amount of superheating. The refrigerant vapor will leave as a superheated vapor. Low pressure, we're still on the low pressure side. We're still on the low temperature side, but now we have a superheated vapor. Okay. So the air that passes into the evaporator through the fins around the outside of the copper tubes or pipes. That loses its heat energy to the refrigerant, and it will come out colder, and that will then pass into the room, hopefully collecting more heat energy, reducing the temperature or removing heat energy from the cold space. Okay, so back to our temperature enthalpy chart for the low pressure side. So we will use our low pressure gauge connected to the low pressure side to get the low pressure. So our low pressure is going to be taken to a refrigerant table, whichever refrigerant's in the system, and that will then be used to obtain the saturation temperature for our refrigeration evaporator. Okay, and that is the temperature that is occurring there. Okay, so that is the main part of the activity happening in the evaporator, is this heat energy being absorbed into the refrigerant. So this is a latent heat energy transfer, and it is causing the refrigerant to change from a liquid to a vapor, change of phase. The last part of the evaporator was superheating, and just like for subcooling, the same applies for the superheating. We need some kind of temperature sensor to measure the pipe of the evaporator outlet, and with that temperature we will plot it on the temperature enthalpy chart, and it can only be warmer. It can either be the same as the saturation temperature or warmer. So if everything's working correctly, if the temperature is warmer, we go up, and we can then come across and we can plot exactly the temperature on the temperature enthalpy chart, and that will be giving an indication of the superheat value. And the superheat is allowing us to remove a little bit more heat energy from our refrigeration system. So that is the application of using our pressure gauges and a temperature sensor to measure the pressures and the temperatures of the system. So just to recap quickly, we use the low pressure gauge, and it has to be the absolute value. We go to our vapor tables, and from our vapor tables the corresponding temperature will be our saturation temperature, and that temperature is running along the horizontal line, the line inside our evaporator. Okay, so the main way that we are shifting heat energy in a refrigeration system is by means of latent heat energy transfer. Having a superheat value after the evaporator is good because it means that we are maximizing the refrigeration effect across our evaporator, but at the same time we're protecting our little compressor from trying to compress an incompressible liquid. Okay, so superheat is very desirable in a refrigeration system. Subcooling, it's desirable from a maximizing refrigeration point of view. It's also making the system work a little less hard to move the heat energy, but definitely superheat value is important. Moving along.